Hello, good morning. Let's start with statistical methods. So, the bigger topic now is the complex Fourier series. So, in terms of the intuition and the overall content, not much changes. So we are still kind of in this process of being given a function f. So let this be f. And we want to figure out how the amplitudes of different frequencies that we find in this function, and then have a frequency domain representation of f where we have frequencies, and then we can say, okay, in this function there's that and that much of this frequency, and there's maybe less of this frequency and less of this frequency, and then we have this kind of Fourier frequency domain representation of this function. And we've made a little bit of progress last time with regards to that, because what we established is to write a function that satisfies a certain set of conditions, which are these Dirichlet conditions. One of them is that the function is periodic. With period t, we found for functions of this type that we can actually write this as a linear combination of generalized sine and cosine functions when we use these frequency terms k over t, where t is the period of the function. And to write this in this Fourier series form, which roughly has this kind of format where you have ak and bk being the coefficients, and the sine and cosine functions being kind of the basis functions. If you have this Fourier series representations, we found that we have now closed formulas, or formulas, let's say, for the coefficients, and we found that a0 is 1 over t, with the function of interest being integrated over this interval minus t half to t half. We found a formula for ak, which is of this form, where we have f times essentially the cosine. So I'm abbreviating things here and being a bit sloppy, but just to remind you, for bk we found a formula where the sine plays a role, and that's about it. And of course these are always dependent on the specific frequency that we're interested in. And that's all fair enough. And these coefficients, of course, they represent the amplitude of these linear generalized sine functions in the real Fourier series representation, and they are something that we can, for example, plot here. So for a given frequency, we could, for example, add the ak and the bk, and then say the amplitude of this frequency is ak plus bk, and then plot it like this. This could be done. It's not quite what is done. And to get to the actual mathematical operation of interest, which is the Fourier transform, which we haven't discussed yet, we only discussed the real Fourier series. We need to, unfortunately, if you want to take that stance, we have to rewrite the real Fourier series form. Can you close the door, please? In the complex exponential way. And the reason why we have to do that is mainly because the entire literature uses this representation. So the fundamental thing in this whole thing is essentially this equation, that the exponential with the complex number I times x is the same as the cosine of x times the complex number I times sine x. This is kind of the fundamental thing that we need to discuss. And what I was about to say is that the technical literature uses this formulation of the combination of cosine and sine functions quite a lot. And the Fourier transform is formulated as that. And also, yeah, if you deal with MRI, you get this signal that you acquire is typically a complex number, which also goes back to the fact that this complex exponential can express cosine and sine functions and their sums. So so the complex form of the Fourier series doesn't change things in any conceptual way. The whole thing is about finding the amplitude of frequencies in a given function, and the only thing that it changes is the notation. And what we want to do then today is to basically look into some detail into this change of notation, so that it makes sense, and that when you see essentially this exponential with a complex number in it, that you know what is meant by that. Yeah. Good. Anything to discuss from last time that you feel you need to discuss now? No. The mathematicians are not there. So who has seen complex numbers in school? No. In your bachelor degree, what did you do? And
just one.
And what kind of degree did you have?
Psychology.
Psychology. And you did linear algebra. Why?
Because I'm interested.
That's very good. Was that mandatory in your psychology degree? No, you just went to the linear algebra. Yeah, everybody should do that. And everybody should also go to the calculus stuff. Good. Very good. So maybe if you saw complex numbers in linear algebra, though, because when I saw them in linear algebra, they were a little bit more abstract than the way we look at them here now, because we look at them from a fairly applied perspective to basically get to this complex exponential. So in linear algebra, the way I learned about complex number there was kind of as a another type of I think it's called field. So there are these in math, there are these mathematical entities where you can compute, like Ringe and stuff. Was it something about that? Ringe, something. Ringe and these other things. Anyway, we use a fairly applied perspective on complex numbers now. Good, and this is what we're going to do. So we start with kind of a tutorial, brief introduction to complex numbers, and then we're going to talk about the Euler formulas and Euler identity, which establish this connection between the exponential and the cosine. And once we are done with that, we will talk about the complex form of the Fourier series. So to introduce complex numbers, what one can do is actually go back to something that you definitely have seen in school, namely the solution theory for quadratic equations. So I think every one of you in school dealt with equations of this form. So you have a known constant A and a known constant B and a known constant C, and then the sum of A times x squared plus B times x plus C is supposed to be 0. Of course, you can also put the C on the other side. Then you have the x on one side and something not necessarily 0 on the right-hand side. And in school, you solve these kind of equations. Does anyone remember kind of the formula, the name of the formula that you use? Maybe not the form of the formula, but the name? Beta? Alpha, beta, gamma. I think you said PQ formula. Yeah, and I was after PQ formula. In school we didn't, so in my high school years we didn't actually learn about the PQ formula. We solved this thing with what was called quadratische Ergänzung, which was essentially kind of a longer but maybe a little bit less formula-driven way to solve these equations. However, here I will start with the PQ formula. And we will not now go about how to solve these equations, but we assume that everybody of you knows the PQ formula. So it's called PQ formula. I think in general they write like this or something. So if you don't know what this is, please Google it and remind yourself of your high school algebra. You've seen this. Maybe it wasn't called PQ formula, or maybe it was called something else. Maybe it had something to do with your beta alpha. Can be, I am not quite sure what you meant by that. So this PQ formula, what it comes down to, and this is where we start now, what it comes down to is that it gives you a formula to solve these kind of equations, and these kind of equations always have true solutions, which you can compute based on this formula, which you derived in high school, or you used some other way that essentially is equivalent to these formulas to solve these equations. Essentially, it's the minus b plus minus, so something like this. These other things, so I'm just writing it out all the way so that you see that there are two solutions. So this is kind of the formula. There's a C missing. And that's about it. So these are formulas. If you know A, B, and C, and the framework and the game or whatever is that you know these numbers, then you can compute two solutions to this equation ax squared plus bx plus c, which you can compute based on these formulas, which on the right-hand side obviously only have the constants a, b, and c. So far, so good. However, this obviously involves a square root here, and you might remember from school, I don't know how explicitly it was communicated there, that you can take square roots of positive numbers. So if you, for example, have 4, then the square root of 4, oops, that's 1, 2, 3, 4, so that would be 1, 2, 3. The square root of 4 is 2, square root of 1 is 1. And you get this kind of graph for the square root function, but this is only defined on the positive numbers. So if you had to take the square root of, let's say, -4, you should not know what to do, and ideally you would also not come up with something besides the complex numbers, because the way that square roots work is that it's the number that, if you square it, yields the number under the square root. So for example, if you do the square root of 4, then 2 square is obviously 4, so that's then the square root of 4. If you do the square root of -4, you would have to square something and get a negative number, and if you are in the real numbers, then that doesn't exist, right? So if you have negative numbers and you square them, then you get something positive, which you also know because you looked at this the square function quite a lot. So that's an example for a function that is not bijective, it's not a one-to-one mapping. And these functions are in general not invertible. However, on certain subdomains, for example, here on the positive numbers, you can invert them, and then you have the inverse of square is the square root. You know that, but what I emphasize here is that that only works for positive numbers that you take the square root of. So I hope everybody agrees with that. If not, raise your hands now or be silent forever. In this regard, not in other regards. Of course, you can say something in other regards. Okay, so everybody's happy with the fact that you can take square roots of positive numbers. Now, when you look at these formulas, of course, what can happen is that you have the case that the term that you're supposed to take the square root of, so this b square minus 4ac, is actually negative, so smaller than 0. And this would not work if you are just dealing with real numbers, because you can only take square root of positive numbers. Now in school, I guess you never ran into that problem that you couldn't really solve this quadratic equation, or at least I never ran into that problem, because our teacher made sure that all the quadratic equations that we actually solved were of such a form that this is not the case. I think we didn't really discuss that they don't have a solution. Maybe we did, I don't remember. But we definitely didn't discuss square roots. However, this can quite easily happen. So for example, if you think of the quadratic equation x squared minus 2x plus 2 equals 0, then our b square minus 4ac evaluates to minus 2 square, so that's the b. The b is negative here, square, minus, minus 4a, what is a? A is 1, c is 2 times 2, so we get 4 minus 8, and hence minus 4. So if we now want to use our formula that we found above, that we didn't find, but we were given here above, we would have to take the square root of minus 4, and that does not exist if we are dealing with real numbers. So what then, what can be done? Well, we might want to invent new types of numbers, which are called complex numbers, to be able to solve these kind of equations. Yeah? So there are many applied examples where you are in math led to quadratic equations again, so they are quite fundamental, which is why you also get taught about them in school. And you can also have the case that they are of the type that cannot be solved within the real numbers. So one might want to invent new types of numbers, which are the complex numbers. Now, the most important thing about this whole complex number business is the invention of the imaginary unit, I. So that's called, maybe do it the other way around, imaginary unit. And this is just a definition. So I, sometimes it's also called J, but in general it's called I, is defined as the square root of minus 1. Yeah, and there you don't have to think much about what this is supposed to mean. What you need to appreciate is that if you square I, you get -1. So if you do I square, which is the same as square root of -1 square, you get the thing under the square root, which is -1. Yeah. So that's completely analogous to if you, for example, if you do, for example, 4. Do I want to do this? Square root? No, it doesn't really matter what I do here. So that's generally true, but what I am trying to figure out right now was to give an example. So if you do, it doesn't really matter. So if you do square root of 2 and you square that, then you have square root of 2 times square root of 2, which is the square of square root of 2, and this is just 2. Yeah. So what I'm just trying to emphasize is that if you have a square root and you square it, then you get the thing that's under the square root. Yeah. So that's here as well. And that's the most important thing. And if you want to be happy with complex numbers, what you need to remember from now on is that I is defined as the square root of -1. And if you square I, and that's maybe even more important actually, if you square I, you get -1. That's kind of the crucial thing. So the most important thing is actually if you square I, you get -1. If you remember that, you can now compute with complex numbers, although you might not be aware of that now. But remember, I square equals -1. So the imaginary unit then can be used to write all kinds of square roots of numbers. So for example, above we here came to our -4. So if we are now supposed to compute the square root of -4, if you remember the rules of exponentiation, maybe you want to look into them in terms, not in terms, but in the PMNAF early sections, then you know that square root is the same as to the power of 1/2, and then it's quite obvious what you can do with square roots. It's, at least for me, that's always more obvious than if you have this square root symbol that you're allowed to, for example, take them apart as I'm doing now. So the square root of -4 is the square root of -1 times 4, which you can take apart. So because it's this fact, or this term times this term to the power of 1/2, which is the same as this term to the power of 1/2 times this term to the power of 1/2. So you get square root of -1 times square root of 4, which you can then write as square root of 4 is of course 2, and we just defined that the square root of -1 is I, so you can write square root of -4 as 2i. Yeah. And that works just because you take the minus sign. So if you have positive numbers and you take the square root, you don't have to do anything. If you have negative numbers and you take the square root, then you have the minus sign in front of it, which you can regard as -1, and then you can take can basically break up the square root. Then you have always this factor square root of -1, which is now called I, and then you can write the square root of a negative number as a complex number, or at least let's say, because we will have to define what complex numbers really are, at least as in terms of this I thing. Yeah. Questions so far? No? Good. Now, with these new numbers here, this 2i, one can then actually compute, and we want to do that. So we want to solve now our quadratic equation. So let's write it up again. So our quadratic equation was x squared minus 2x plus 2 equals 0. Our PQ formula, now I'm writing it in 1 so that I don't have to write too much. Let's save a little bit of energy. Plus minus b squared minus 4 AC divided by 2A. That was our formula for solution. And now we can basically plug things in. So x1, we need, so remember this is the factor in front of the x square, that's the A. The factor in front of, oh, geez, no, this is starting it. The factor in front of the, let's put it here, A, B, C. So the factor in front of the x square is our A. The factor in front of the B is our of the x is our B. So our formula looks as follows. So minus B, that's plus 2, because B is minus 2. And then I'm first doing the negative one, so have the minus instead of the plus there. Then we computed already this, because that's set off the whole thing, so that was square root of minus 4, and A is 1, so we have to divide this by 2. And then we saw that we can rewrite the square root of minus 4 as 2i. Just saw that. And then we can kürzen, which yields 1 minus I. Yeah? So we basically divide 2 by 2 and this, and then we get 1 minus I. Yeah. So one solution for this quadratic equation, this is kind of the message here. So that's solution 1. And then solution 2, the difference is that we have to take the plus here, and this then yields the same thing with a plus 2, and here we have I plus I. So that's our solution 2. Yeah, so we have found two solutions now, one being 1 minus I and the other one being 1 plus I. And of course, one might want to check whether these are really solutions, because, I mean, the whole framework says these are solutions, but better make sure that they really are. If we now plug that in, this is also what you did in school. Let's do that maybe for one of them. So, don't know, is that easier? I guess it's easier with the plus, then we don't, the chances of sign errors may be minimized. So if we plug that in into the quadratic equation, we get 1 plus I square minus 2I 1 plus I plus 2 equals 0. Now we're going to check whether this is the case, or maybe let's do it differently. This is what should come out, but maybe let's just actually see what comes out. So I plus 1 plus I square is 1 square plus 2 times 1 times I plus I square minus 2 times 1 plus 2I, that was a minus, plus 2, if I'm not mistaken, plus, minus, oh. So that's 1 plus 2I, and now what you really need to remember is that I square is minus 1, so this is minus 1, minus 2 minus 2I plus 2. So we have plus 2I minus 2I, 1 minus 1, and minus 2 plus 2. So that's 0, which shows that this one is actually a solution of that one. And you could do the same thing, and this is also documented in the script for the I minus 1. And the crucial thing to show that this is the case was actually this here, so that I square is minus 1. then it works. Yeah. So this is kind of a motivation to say, okay, there are quadratic equations which we cannot solve if we only deal with real numbers, because we have to take the square root of negative numbers. So we need to come up with kind of a different number set that allows us to find solutions and define solutions for quadratic equations, so that we can use these solutions of quadratic equation for something else. So this is kind of a motivating example. And now we want to look at complex numbers more from a now as a mathematical entity with some definitions. Yeah? Questions about this business of computing right now with complex numbers in this little example? No. Good. So that was kind of the motivation. Now complex numbers in a nutshell, essentially. So complex numbers, so you are familiar, of course, with some sets of numbers, I hope, because you watched the videos and you studied the PMFN sections on that. So you are familiar with the natural numbers, the integers, the rational numbers, and the real numbers, and we also briefly discussed them. And in addition to that, we now come up with a new number set, which are the complex numbers, for which this C symbol is used. Maybe I write that better here. So that's this C, as in complex. And complex numbers are of the following general form. C is defined as the set of all A plus I B, where A and B are real numbers and I is the square root of -1. So the only thing changed now is that previously we had this complex number 2i. This actually here the A, if you now look at this definition of complex numbers, here A was 0 and B was 2. Yeah. So then this is a complex number. However, what will be called the real part, so this A was 0 for this complex number. Was a special complex number. But in general, the complex numbers are defined as this. And of course, the B can also be 0. So if the B is 0, then if we have B 0, then of course we have the complex number. Usually complex numbers are denoted by Z's. Z A plus I times 0 is A, and A is a real number, so the complex number Z is then also a real number, which means that the real numbers are actually a subset of the complex numbers. So if you want that very intuitive, is that the complex numbers contain the real numbers as a subset. Yeah? So the complex numbers, so if these are the complex numbers, then the real numbers are a subset of them. Yeah. So and formally you can write it as this. Good. So this is the general definition of complex numbers, and so a general complex number would then be something like this: A plus IB, where A, B are real numbers and I square root of -1, as it says just one line above. And then with these real numbers in linear algebra, for example, in math, one goes a little bit into computing with them and stuff. We also go a little bit into computing with them, but there they can also be defined quite differently without this imaginary unit and so on. That's not what we are after here. We are kind of in the applied setting. So there are then some definitions that come with them. And the first things that I also briefly mentioned are the real part and the imaginary part of a complex number. So the real part of a complex number z, which is often denoted as this, real part z, it's kind of a function applied to a complex number, and the function is called re for real part, and the output of this function is a. So basically the real part of a complex number is this a, which then makes it quite intuitive that the complex part of a complex number, which sorry, not the complex part. Why do I call it the complex part? Don't know. It's usually called the imaginary part. Doesn't really make sense to call it complex part. The imaginary part. So there's a real part and an imaginary part. So don't even start thinking about imaginary, like imagine something, and real, like being something real or something. That completely doesn't help here. Just use it as names. So the imaginary part is the b. It's the coefficient of the imaginary unit. Yeah. So it makes a lot of sense that that these things are called that way, and it's also fairly trivial, right? So the real part is this a in the complex number, and the imaginary part is the b in this complex number. Now, one thing that will haunt us for a long time, especially the notes in January, is that the real part and the imaginary part of a complex number are both real numbers, right? So a and b are by definition real numbers. So one can actually represent two-dimensional vectors of real numbers, so things in R square, so vectors of the form AB, yeah, so where A is a real number and B is a real number, one can represent them by complex numbers, yeah, and if one wants to write this a little bit formal, one can write that there is a bijective mapping between the complex numbers and the real numbers. So, sorry, not the real numbers, the complex numbers and the two-dimensional real vectors. A bijective mapping just meaning that it's a one-to-one mapping. So if you give me a two-dimensional real vector, I can give you the corresponding imaginary number. The corresponding complex number. If you give me a complex number, I can give you the corresponding two-dimensional real vector. Formally, one may want to write this like this. So if you have a function from the complex numbers to the two-dimensional real numbers, so you put in a complex number, then this function outputs a two-dimensional real vector, and if z is actually written like a plus ib, then of course this is ab. Now if you invert this function and do go the other way around, so go from r square to c, then you take a vector AB and map that onto a complex number A plus IB. So now very intuitively, so of course vectors in 2D, so points in 2D have this form, and if you have here the x and the y, you might call this whole thing the transverse plane. Remember fMRI stuff, not complex, transverse plane. So the thing where you measure the MR signal, and if something is moving in here, so if you have a vector that shows some movement in here, for example turning or something, then you can describe this as a vector that changes its behavior over time, or you can write this as a complex number that changes its behavior over time. The difference is not that one or the other has more or less information, it's just a different kind of notation. Yeah? So this kind of going between two-dimensional vectors and the real numbers and complex numbers is fairly trivial because it's based on this stuff here, and but it will be quite important when we talk about the actual MR signal dynamics in general. Yeah, for now we don't really need this that much, but also as a further motivation to look into complex numbers. Of course, this is closely related to the stuff that we do with complex exponential, but yeah, we will not see this in this explicitness until February and March or January. Things will be awesome. Good, so this is the real part and the imaginary part, which allow for this one-to-one mapping between the two-dimensional real numbers and the complex numbers. And yeah, then there's this absolute value of a complex number. Maybe we briefly write that up. We will not need that much right now. So the absolute value of a complex number, which also allows to see some parallels between complex numbers and polar coordinates. Yeah. So there are polar coordinates and then circular coordinates in 3D. Am I doing it the right way? I guess. Then so the absolute value is kind of the length of the complex number, but don't think too much about it. It's just defined as the square root of a square plus b square, and the argument of a complex number defined as the arcus tangens of b divided by a. So they don't really help much right now. I'm just for completeness, I think I'm mentioning them. The conjugate of a complex number, I think we actually need. So the conjugate of a complex number, so if z is a plus aib, then the complex conjugate or the conjugate of a complex number is usually written as z with a bar above its head, above z, and is just defined as a minus ib. Yeah, so if you have a complex number and you know, for example, a is 2 and b is 3, then the complex conjugate of 2 plus 3i is 2 minus 3i. And one can actually quite easily show that, and that's 115 with 115 equations in this chapter. One can quite easily show that a complex number times its conjugate always yields a real number, because that's a square plus b square. So you see the little steps in between in 115, or maybe it's a different number because you printed out in the earlier version. Remember, this is a living document. So the z times z conjugate is a real number. Good, but I think that's where I want to stop this, and also because I don't have any more material on this. So the next thing then would be to talk about Euler's formula to relate now the complex numbers and the exponential cosine and sine. So essentially, these are all just definitions. This is vocabulary, so you just need to learn the vocabulary if you want to be happy with this, and you need to be happy with this. And you can kind of, if you want to know why complex numbers, you can say, okay, so that we can solve certain quadratic equations. So, and then complex numbers are just there, and then you can see, and we can see what we can do with them. Yeah? Questions right now? No. So far so good. No panic attacks or anything because of complex numbers. That's good, but a question.
What exactly is this conjugate, this argument? I don't really get this.
Yeah. So conjugate, conjugate would. So the argument, or actually, so the argument you can view as an angle for a complex number. Why it's called argument, I'm currently not sure. Does anyone know why it's called argument? but you will find, look on Wikipedia why it's called argument, you will find a good reason why it's called argument. The conjugate, that's, what's the main motivation? I think we will, do we need them? I'm actually not quite sure whether we will need them. So the thing is, you can, in math, you can always kind of define this kind of anti-element. So for example, if you have, something like x equals 2a, then to get to what x is, you need to divide by 2 or multiply by 1/2, and 1/2 for 2 is the reciprocal or the multiplicative inverse. Now the conjugate is not really any inverse of a complex number, but it's another element in the complex numbers that if you apply that to a certain element, something of great importance or great value maybe in some situation happens because you get a real number.
So it's just a tool.
It's just, yeah, you can see it as a tool. Yeah. Although it's not really a tool, it's just another element in the complex numbers. So the conjugate itself is a different element in the set of complex numbers, but one can use it as a tool in certain contexts.
It's probably understood by using it, I suppose.
Exactly, yeah.
Okay.
That's the whole thing with all definitions in math, that, of course, yeah. So definitions and so on, they always get their value from what follows from that. Yeah, anything else? No. Yeah.
I don't know if this is a question, but what if b is negative?
What if b is negative? Well, then if b is -2, for example, then you have a minus 2i. So b can be positive or negative. It's a real number, and the complex number is defined as a plus ib, and if b is negative, or ib, then you get a negative sign here. And then for the complex, of course, you need to, for the complex conjugate, you need to take the negative again. So it's then the conjugate is a plus 2.
Actually, the reason I asked this was because it is very elementary maths, but to a plus b and a minus b, when we multiply this, we generally get a square minus b square. And in this case, we're getting a square plus b square because I understand that I square will be -1, so it will convert it into a square plus b square. But in that case, if we actually ever get -2, then the minus of the b will also disappear somewhere when we multiply complex conjugate with complex.
Yeah, that's actually what happens in the. That's what actually. So what you describe is what I went over quite briefly with the complex conjugate here, and for the details of what you just described, that's in the script. So I didn't write them out, but it's actually what you just described, essentially what happens. Yeah? Okay, so let's have a break and continue then briefly after 9.